In the world of military aviation, few aircraft have captured the imagination and respect of engineers, pilots, and aviation enthusiasts like the F-14 Tomcat. Designed during the Cold War, born out of political tension, technological ambition, and strategic necessity, the F-14 was not just a fighter, it was a symbol of American air power and engineering brilliance. The story of the F-14 Tomcat is not just one of speed, weapons, or design. It is a story of engineering ingenuity pushed to its limits. The F-14 Tomcat was developed by Grumman Aerospace, a company with a reputation for building rugged naval aircraft. It was born from the failed F-111B project, a Navy version of the Air Force's F-111 Aardvark, which proved too heavy and ill-suited for carrier operations. The Navy needed a new air superiority fighter, one capable of long-range fleet defense, dogfighting agility, and carrier-based operations, a rare combination that demanded a revolutionary approach to aircraft design. What emerged was an aircraft unlike anything the Navy had flown before. At the heart of the F-14's engineering marvel is its variable sweep wing. This design allows the wings to move between different angles, or sweeps, in flight. At low speeds, such as takeoff, landing, or during tight maneuvers, the wings sweep forward to increase lift and stability. At high speeds, they swing back like a dart to reduce drag and allow supersonic flight. Controlled automatically or manually, the sweep angle ranges from 20 to 68 degrees. This adaptability gave the Tomcat unmatched versatility, allowing it to dominate dogfights and cruise efficiently at high speed and altitude. Such a mechanism isn't easy to engineer, especially when operating from an aircraft carrier where space, weight, and reliability are crucial. The wing sweep mechanism involved heavy-duty pivot points and hydraulic actuators, precisely engineered to withstand repeated stress and extreme flight conditions. The wings themselves were built with a high-strength titanium alloy structure to endure both the aerodynamic loads and the stresses of carrier landings. But the wings were just the beginning. The F-14 Tomcat was among the first aircraft to incorporate a twin-tail vertical stabilizer design, giving it better control at high angles of attack and improving its overall maneuverability. Its fuselage was wide, housing powerful twin engines and a tandem cockpit for the pilot and radar intercept officer. The size and structure of the fuselage allowed it to carry a revolutionary radar and weapons system, the AWG-9 radar, developed by Hughes, which was decades ahead of its time. The AWG-9 was the first radar system that could track up to 24 targets simultaneously and engage 6 with long-range AIM-54 Phoenix missiles. This gave the Tomcat fleet defense capabilities like no other aircraft. The AIM-54 was a massive missile, 13 feet long and weighing over 1,000 pounds. It could engage enemy aircraft from over 100 miles away at speeds exceeding Mach 5. Integrating such a large and powerful weapon into a carrier-based fighter required incredible coordination between radar, flight control systems, and missile fire control software, an engineering challenge on a scale previously unseen. Inside the cockpit, the division of labor between pilot and radar intercept officer was critical. The pilot flew the aircraft, while the RIO operated the radar and managed weapons. This allowed the Tomcat to fully exploit the capabilities of its sensors and missiles without overwhelming a single operator. The cockpit featured multi-function displays, hands-on throttle and stick controls, and analog instruments designed to work even under high G-force conditions. Speaking of power, the engines were both a triumph and a challenge. The original F-14A models were equipped with Pratt & Whitney TF-30 engines, which were actually designed for the F-111 and proved underpowered and prone to compressor stalls at high angles of attack. These issues led to several accidents and required careful throttle management during air combat. However, later models, like the F-14B and F-14D, were upgraded with General Electric F-110 engines that vastly improved performance, reliability, and thrust-to-weight ratio. With these engines, the Tomcat could exceed Mach 2.3 and climb like a rocket. Carrier operations added another layer of complexity. The F-14 had to endure the violence of catapult launches and arrested landings, tasks that place enormous stress on airframes and landing gear. The engineers reinforced the nose gear, designed a dual-wheel main gear for better load distribution, and included an arrestor hook system tough enough to survive hundreds of landings on a moving, pitching flight deck. The aircraft's tailhook and landing gear mechanisms were hydraulic masterpieces, balancing shock absorption, strength, and weight efficiency. One of the often overlooked aspects of the F-14's engineering is its avionics cooling and maintenance systems. The Tomcat was built to be modular. Each component of the avionics system could be removed and replaced easily by deck crews. Its cooling systems had to manage the massive heat load generated by the radar and mission electronics, especially in the confined and hot environment of a carrier hangar deck. Grumman engineers designed the systems to be accessible and survivable, minimizing downtime and maximizing sortie rates. Aerodynamically, the Tomcat was a beast. Its large lifting body contributed to overall lift, and its large, flared engine nacelles improved high-speed airflow. Engineers incorporated vortex generators and aerodynamic refinements that kept the aircraft controllable even at high angles of attack. It could pull more than 7 gigaseconds in a turn, and its top-end speed and climb rate put it in a class of its own for decades. The F-14 also carried AM-61 Vulcan 20mm cannon, a rotary barrel Gatling gun that could fire over 6,000 rounds per minute. This added a close-range dogfighting punch, ensuring the Tomcat was just as lethal up close as it was at long range. Integrating the gun into the aircraft structure required careful attention to vibration, ammunition feed reliability, and aerodynamic fairness. Over its service life, the F-14 was upgraded with digital avionics, improved displays, GPS navigation, and modern data link systems. The final F-14D models represented the pinnacle of the design, featuring glass cockpits, infrared search and track systems, and improved radar and electronic warfare capabilities. Despite being designed in the 1960s and flying in the 1970s, the Tomcat remained relevant into the 2000s, a testament to the forward-thinking engineering that built it. The legacy of the F-14 is not just one of combat missions, iconic movie appearances, or Cold War symbolism. It is a legacy of what happens when engineers are given a tough problem and the freedom to solve it with ambition, creativity, and precision. Every rivet, every hydraulic line, every line of code in the Tomcat represents a decision, an engineering solution to a complex challenge. When the last F-14 retired from U.S. Navy service in 2006, replaced by the more modern but less awe-inspiring F-18 Super Hornet, it marked the end of an era. Yet the Tomcat continues to fly with the Iranian Air Force, and continues to live on in the hearts of aviators and engineers alike. It wasn't just fast. It wasn't just deadly. The F-14 Tomcat was a flying laboratory, a machine of astonishing complexity and bold innovation. The F-14 Tomcat represents a pinnacle of Cold War-era engineering, combining variable sweep wings, advanced radar systems, and carrier-capable design to create one of the most versatile and iconic fighter jets in aviation history. Developed during a time of intense geopolitical tension and rapid technological advancement, the Tomcat was conceived not only as a superior dogfighter but also as a long-range fleet defense interceptor, a dual-role capability that placed immense demands on its design and engineering. The variable sweep wing system alone was a groundbreaking feature, allowing the aircraft to dynamically alter its aerodynamic profile in flight, sweeping forward for increased lift and maneuverability at low speeds and extended wingspans, and sweeping back to reduce drag at high speeds, enabling sustained supersonic performance. This adaptability gave the Tomcat a distinct tactical edge, making it effective in both close-range combat and high-speed interception missions, a versatility rarely seen in naval aviation up to that point. Beyond its airframe and aerodynamic innovations, the Tomcat was equipped with the AWG-9 radar system, an immensely powerful piece of avionics hardware for its time. This radar allowed the F-14 to detect, track, and engage multiple enemy targets at ranges exceeding 100 miles, a capability unmatched by any other fighter in the U.S. arsenal at the time of its introduction. It worked in conjunction with the AIM-54 Phoenix missile, a long-range air-to-air weapon that could strike targets well beyond visual range, giving the Tomcat an unparalleled reach in aerial combat. The integration of this radar and missile system transformed the F-14 into a flying sentry for carrier battle groups, capable of intercepting threats far before they could come close to U.S. naval forces. This required the aircraft to carry not just brute force, but also an incredibly sophisticated command and control capability, managed by the tandem cockpit layout that separated pilot and radar intercept officer responsibilities, ensuring optimal mission performance in high-stress combat environments. The structural integrity of the aircraft had to meet extreme standards, given the demanding nature of carrier takeoffs and landings. Grumman Aerospace engineers crafted a robust airframe with reinforced landing gear, tail hooks, and wing structures that could withstand the intense forces of arrested recoveries and catapult launches at sea. Every component, from its titanium wing pivots to its twin vertical stabilizers, was meticulously engineered to endure harsh maritime conditions and repeated high-G maneuvers. The inclusion of twin engines added a layer of redundancy and power that further increased the aircraft's survivability and thrust, allowing it to accelerate quickly and maintain superiority in vertical and horizontal engagements.